Hi there, Mr. Sutton bringing you these AB Calculus Chapter 4 Quiz 3 review solutions on mean value theorem, linearization, derivatives of inverses, and L'Hopital's rule. For this problem, we're trying to find all values of x on this interval here that satisfy the mean value theorem. So basically, we're trying to figure out all the x values where the instantaneous rate of change at those x values equals the average rate of change for this function across this whole interval. But before we do that, we have to figure out if this function even could satisfy the mean value theorem by looking at the conditions. So mean value theorem, to work, your function has to be continuous on the closed interval and differentiable on the open interval. And this is a polynomial, so it is both continuous and differentiable on this interval. So we go ahead now and we're going to do the average rate of change. So that's going to be f of 3 minus f of negative 5 over 3 minus negative 5, or 3 plus 5. F of 3, well, that's going to be, 27 plus 15, which is 42, minus 4. So that's going to be 38. And then if we're doing f of negative 5, that's going to be negative 125 minus another 25 minus 4. So that's going to be negative 154, but we're subtracting it, so we're going to actually be doing plus 154. And of course, down here we've got 8. So 38 plus 54, that's going to be 192. Dividing that by 8, that's going to end up being, well, let's see here. 200 divided by 8 would be 25, so 8 less than that, you've got 24 altogether. 192 over 8, 24. So that's the average rate of change we're now going to try to match up with the IROC, the instantaneous rate of change. So next we have to find the derivative of our function here, which is 3x squared plus 5. And we have to set that equal to 24 and solve. Oops, there we go. So set it equal to 24. So subtract 5, and we're going to divide by 3, and then square root everything. So we're going to end up getting x equals plus or minus radical 19 over 3. So just to do a quick check, and you have to check at the end here because you might have values that don't work, you need to make sure these values are actually on the open interval from negative 5 to 3. Now these both are. 19 over 3, well, that's pretty close to 18 over 3, which would be 6. And the square root of 6 is going to be somewhere between 2 and 3. So that's definitely going to fall in between negative 5 and 3 without being an actual value on the endpoints there. It is important to note, so this is true. We make sure both of these are in the interval. It is important to note here that negative 5 and 3 specifically would not be acceptable. If you got exactly 3 for an answer, for example, because that's not on the open interval, it actually would not satisfy the MVT. And I know the AP exam occasionally throws a question on there where that's one of the options and you want to throw it out. For this next problem, we have a table here showing the number of mini chocolate bars in a candy jar at a wedding reception after a certain number of hours. We want to use the data in this table to approximate the rate at which the number of chocolate bars is changing at time 3 hours, and then show your computations leading to your answer. So if you're trying to approximate an instantaneous rate of change, which is what you're asking for, if you're asking for the rate specifically at time 3, but you just have a table, you can still approximate this by finding the average rate of change for an interval on which 3 lies. So, for example, we could find the average rate of change between time 2 and time 5. Technically, you could do any times as long as 3 lies between those times. But really, you should just pick the closest ones, which would be 2 and 5. So we're going to do f of 5 minus f of 2 over 5 minus 2. And we don't have an f function, actually. I misspoke. It's the r function. Make sure you actually use the name of the function they give you. So this is going to be 23 minus 47 over 5 minus 2. So that's negative 24 over 3, which is negative 8. Now, this is a real-life problem, so you do need to have units on this. What units should we have for the rate at which chocolate bars are changing? Well, the output is chocolate bars, and the input is hours, so we have basically negative 8 chocolate bars per hour. That's the rate at which the chocolate bars are changing. For this problem, we're going to use linearization to approximate a function here. So we're trying to approximate the value of pi over 4 minus 0.3 f of that, where the f function is e to the cosine of 2x. Now, needless to say, this is impossible to find the closest value, the decimal value of, without a calculator, but we're going to get pretty close using a tangent line at x equals pi over 4. Why? Because that's what they told us to do. All right, so our linearization formula is right here. We've got L of x equals f of a plus f prime of a times x minus a. This is essentially the point-slope formula, just modified a little bit. This f prime is your slope, x minus a and L of x minus f of a, that's giving you your point, your x and your y values. So to get all this stuff, we need a few things. I'm going to start by finding f prime. So let's find f prime of x in general, and then we'll find f prime of pi over 4 specifically. So in general, we're going to need the chain rule on this. The outer function is just e to something. So my first derivative on the outermost function is going to be e to the something, which in this case is cosine of 2x. But now I have to multiply by the derivative of cosine of 2x. So the next function in is cosine. That derivative is going to be negative sine of 2x. And don't forget, you still have to take the derivative of 2x. That's the innermost function. So that's going to be a 2 for the tail at the end. Now I'm going to take f prime of pi over 4. So I'm going to move this 2 out in front along with the negative. So I'm going to be doing essentially a negative 2e to the cosine of 2 times pi over 4 times sine of 2 times pi over 4. All this stuff. And this is actually not as bad as it looks at first glance. So sine, let's do this one out here first. So 2 times pi over 4 is just pi over 2. Sine of pi over 2, well, that's just 1. So this is not going to make any difference because we're multiplying 1 by all the stuff over here. So let's look at this stuff over here. Cosine of 2 times pi over 4, well, that's really just cosine of pi over 2, which we know is 0. So we have e to the 0, but e to the 0 is just 1. So we really just have 1 times this negative 2 here. And remember, this stuff here was also just a 1. So when the dust settles, this negative 2 is just getting multiplied by a bunch of 1s to give us negative 2 for our slope. Awesome. Well, now we still need to figure out f of a, the output value at our launching off point here, at our point of tangency. So now I'm going to plug pi over 4 into the original function. And again, we said cosine of all this stuff is really just 0, so e to the 0 just gives us 1. All right, now let's go back and plug it all in. So we can say L of x equals f of a, which we found to be 1 right here, plus our slope at pi over 4, which we found to be negative 2. And then we're just going to have x minus this launching off point, so x minus pi over 4. All right, so at this point, we need to figure out f of pi over 4 minus 0.3. So to show this, I'm going to say L of all this stuff equals 1 minus, and now we're plugging pi over 4 minus 0.3 in here, and then we're subtracting this pi over 4 out there. Now just a quick note on notation. It's perfectly legal to put an equal sign right here because I've defined this approximation function up here. If I were to say f of pi over 4 minus 0.3, then I would have to write a squiggly equals with all this stuff to show that I was approximating and not giving the actual value. So just be careful with how you use your equal signs. All right, so let's see what all this comes out to. The pi over 4s are going to cancel. So we really just have negative 2 times negative 0.3, which is positive 0.6. 1 plus 0.6 is 1.6. So there's our approximation. For this problem, f is a function that's differentiable for all real numbers, and the table up here is giving some values of f and its derivative at selected points between negative 3 and positive 3. And they're also telling us the second derivative of f is negative, less than 0, for all the values between negative and positive 3. Groovy. Based off this, we want to write the equation of a line tangent to the graph of f at the point where x equals 2, and then use it to approximate f of 1.9. And then they want to know if it's greater or less than the actual value of f of 1.9 with a reason. All right, so first things first, let's get our tangent line. So I'm going to whip out the linearization formula here. So we've got L of x equals f of a plus f prime of a times x minus a. This is our standard linearization formula. I'm going to start plugging in some values now. So for this problem, a is our launching off point for the tangent line. So that's x equals 2. We're plugging in 2 for all these a values. So this f of a, we're really just asking about f of 2, which if we look up here is 4. And then f prime of 2 is going to be negative 5. So this is all in the table. And then x minus a really just means x minus 2 in this case. Now we're going to plug in 1.9. So plugging in 1.9, we've got 1.9 minus 2, which is negative 0.1, times 5, negative 5 is going to be positive 0.5, and then 4 plus 0.5 comes out to 4.5. Now, it's worth noting that if this is an AP free response problem, you actually could have stopped after you had all constants here, unless you specifically needed this value for some other purpose. Now, there is a little bit more to this problem. They're asking if this approximation is greater than or less than the actual value of f of 1.9. And the only way to figure this out, since we don't actually know what the f function does at 1.9, is to use this information about f double prime being less than 0. So in general, if f double prime is less than 0, then you've got a concave down, frowny face kind of looking function. That means that any tangent line that launches off of there is going to overshoot the true value of whatever you're looking for. But you have to be careful about how you word this. So to get full credit on this, you have to talk about the interval on which this function is concave down. Specifically, it has to be concave down or concave whatever between the launching off point and the actual x value where you're trying to approximate something. So here's how I'm going to word this. F double prime is less than 0 on the interval from 1.9 to 2, which is definitely true. It's actually less than 0 on a much larger interval, but this is the only one we really care about. Therefore, 4.5 is going to be greater than the true value of f of 1.9. On this problem, we're given some function, and g is the inverse of that function. We're also given that f of 6 equals negative 7, and we want the value of the derivative of g at negative 7. So since we're taking the derivative of an inverse, we're going to use the inverse derivative formula. So g prime of something is going to be 1 over f prime of g of the something. So in this case, 1 over f prime of g of negative 7. So there's a couple things we need to do before we can figure out what this actually is. One is figure out what g of negative 7 is. So g, remember, is the inverse of f. So basically, we're looking for the number that I have to plug into the f function to get negative 7. So over here, I see that f of 6 is negative 7. Therefore, g of negative 7 takes us back the other way to get 6. So we're really just doing 1 over f prime of 6. Okay, what's f prime? Well, here's f. We just have to take that derivative. So that's going to be 6x squared minus 2. So then I'm just doing 1 over 6 times 6 squared minus 2. 6 squared is 36 times another 6 is 216. Minus 2 is 214, so when the dust settles, 1 over 214. On this problem, we're given a table of selected values for f and its derivative. If f inverse, f to the negative 1, is the inverse function of f, we want the value of the derivative of f inverse at x equals 1. So for taking derivatives of inverses, we'll use our inverse derivative formula. So f inverse prime of 1 is going to be 1 over f prime of f inverse of 1. So then f inverse of 1, that's the thing I have to plug into the f function to get 1. So if I look at my output column here, I see that I get 1 when I plug in an x value of negative 3 to the f function. So then f inverse of 1 is negative 3, and we have 1 over f prime of negative 3. And what is f prime of negative 3? Well, we have a table of values giving us the value of f prime at various x values. At the x value negative 3, we get an f prime value of 15. So then this is 1 over 15. For this problem, we're trying to find the limit as x approaches -1 of this expression here. So it's always a good idea to at least mentally see what's going to happen if you plug a number in with these limits. So we've got, this will be 1 minus 9 plus 8, which is 0 in the numerator. In the denominator, we would end up with 1 plus 6 minus 7, which would also be 0. So we're going to end up with one of those indeterminate forms, which means we need to either use L'Hopital's rule, which I'm going to show you on this slide, or some other method of doing it. So if you're going to use L'Hopital's rule, then you need to write here that the limit of the numerator equals the limit of the denominator, and that they both equal 0. You could just write equals 0 on both of them, but this is a little bit faster. So now that means that we're going to use L'Hopital's rule. So using L'Hopital's rule, we're going to take the derivative of the numerator and the denominator separately as if they were completely different functions. So we've got 2x plus 9 for the numerator and 2x minus 6 for the denominator. Now some important points on notation here. If you just wrote up here equals 0 over 0, that would be wrong. We're not supposed to write 0 over 0 because when you're saying this equals 0 over 0 and then you're saying it equals something else, you're saying 0 over 0 equals all those other things, and we don't want that. Another important thing is you got to keep this limit notation. This is still the limit of a quotient here. No limit notation, and you will not get full credit on this. But now that we've taken this derivative, we try plugging -1 back in. And if we do this mentally, we very quickly see we're not going to end up with 0 in both places, maybe not in even one place. So plugging -1 in, this is going to be -2 plus 9, and this will be -2 minus 6. So that's going to be a 7 on top and a -8 on the bottom, so -7/8. Now, another way of doing this problem, for those of you who already saw the L'Hopital's version of the solution, is you can try factoring and reducing and canceling out whatever was giving you 0 over 0. Numerator, we can factor into x plus 1 and x plus 8. Denominator factors into x plus 1 and x minus 7. And then those x plus 1s cancel out. And if you take a quick look here, you'll see that that's why you were getting 0 over 0, because if you plug -1 in for both of these, they both zero everything out. So now we just have the limit as x approaches -1 of x plus 8 over x minus 7. So that's just -1 plus 8, which is 7 on the top, and -1 minus 7, which is -8 on the bottom. So then -7/8 doing it without L'Hopital's rule. For this problem, we're trying to find the limit as x approaches 0 of this expression here. Now, this is one of those where if you mentally check what's going to happen if you plug in 0, we end up with, let's see, cosine of 0 is 1, 2 times that is 2, 2 minus 2 is 0, so 0 in the numerator. 3 times 0 squared is also 0 in the denominator, so this is an indeterminate form. So based on what you've learned this year, L'Hopital's is really the only way to do this. There is another way to tackle this problem using some special kind of trig limit identities, but we're not going to go down that road. We're just going to use L'Hopital's. It's much quicker. So we've got the limit of the numerator as x approaches 0 and the limit of the denominator both equaling 0. We have to show this in the beginning, and then we're allowed to invoke L'Hopital's rule. So now let's use it and take the derivatives of the numerator and denominator. In the numerator, this 2 constant gets differentiated away. It's just 0. And derivative of cosine is negative sign, so that'll be positive 2 sine of x in the numerator. Denominator, this comes out to 6x. And now if we mentally plug 0 in again, well, 2 times sine of 0 is going to be 0. 6 times 0 is 0. So we're again going to use L'Hopital's rule one more time. So I'm going to write the limit of my numerator equals the limit of my denominator equals 0. So using L'Hopital's rule again, we've got another derivative up top. That's going to be 2 times cosine of x. And on the bottom, I'm just going to have 6. Let me try plugging in 0 again. Now I can see right away that I'm not going to get 0 over 0 because the denominator is a constant that's not 0. So plugging 0 in the numerator, 2 times cosine of 0 is just 2. So we have 2 over 6, which is 1/3. On this problem, I'm trying to find the limit as x approaches infinity of this fraction. If you just kind of plug infinity in mentally to see what's happening with this thing, the numerator and the denominator are both going to infinity. So this is one of those indeterminate forms, and we can get rid of that by either using L'Hopital's rule or by using the faster growing function kind of approach, the choose your champion approach that we saw when we were dealing with limits exclusively. Let's do L'Hopital's first, and then we'll look at the other approach. So with L'Hopital's, we have to show that the numerator and denominator are both equaling either 0 or infinity. So I can say the limit of my numerator as x approaches infinity equals the limit of my denominator as x approaches infinity, and that those both equal infinity. Therefore, using L'Hopital's rule, let's take the derivative of our numerator and denominator. So we're going to have just 7e to the x in the numerator. That actually doesn't change. It's its own derivative. Denominator, I've got 18x. And if I mentally plug infinity in again, I'm going to see that the limit of both of those parts is going to be infinity again, especially because we have this variable down here in the denominator. So we're going to use L'Hopital's rule one more time, but again, I have to show separately that my limits are both infinity. I can't just write infinity over infinity. That would be improper notation. So now, taking another derivative, we've got 7e to the x over 18. And notice that I'm keeping this limit as x approaches infinity the whole time. All right, so I can now try plugging infinity in one more time. If I do that, my numerator is still going to infinity. My denominator is just a constant. Infinity divided by a positive constant is just going to be infinity. So this is the other way of tackling that problem without using L'Hopital's rule. This is my non-L'Hopital's rule approach here. And since we're going to infinity, we can use a special kind of reasoning talking about which function is growing faster. So we have an exponential in the numerator and a polynomial in the denominator. Exponential growth is faster than polynomial growth, at least as x approaches positive infinity. Negative infinity, it's the exact opposite. So we would say then that we have a top-heavy function. 7e to the x grows faster than 9x squared. So therefore, this is just going to grow to, since it's a positive overall fraction, positive infinity.